Good afternoon. So we're a confidential computing group from Cyro's Data 61 based out in Sydney, and we work in the area of privacy preserving computation in general. And what we worked on for this week was all about private record linkage and trying to scale that so that we can handle more parties. Essentially, our goal is, can we compute the corresponding rows in 2 or more different data sets? Sounds pretty easy, right? There's a little bit of a constraint that we're concerned that the information we might use for this linkage will have small errors. So there'll be typos and things like that. Secondly, there's a constraint that we have as the confidential computing group that we don't really want to share raw identifiers. Raw personally identifiable information is not what we're working with. Instead, we have an embedding or an encoding of this PII. So this is symbolized here by a vector. In our case, it's around about 1024 bits per entity, and we're computing the distance between them to get our concordance. Another constraint or fact is that it doesn't scale particularly well, in that if we have 1 million entities by 1 million entities, we have to compute the similarity between the pairwise similarity. So we're computing everything with everything. So that's a trillion comparisons if you're just doing a million. Say we're doing 10 million by 10 million, which isn't out of the question in Australia if you're thinking population of states, for example, trying to work out the intersection. And if you're storing those similarities as 32-bit floating point numbers, you have 3.2 petabytes of just similarity scores. So there's a lot of these edges if you're keeping them all. And this only gets worse when you add more parties, because you're having to do party A to B, party A to C, party B to C. So, yeah. The other part of the problem is, once you've got all these many edges, these trillions of edges, to partition it to find out what is the best mapping. Here, where do you cut the graph to work out who is the same entity, which is essentially the problem we're trying to answer. And in a very highly connected graph like we have, when we've got every entity has a similarity, an edge to every other entity, it's very tricky to see how you can break that problem up into parallel or disjoint subsets of the graph that could be computed on in parallel. So we had a look at both of these things this week, both of these stages. So calculating the matrix of similarities is the kind of lower hanging fruit, you could say. Very easy to parallelize. And we had a CPU implementation of this, which has been quite finely tuned and optimized. And we also have a CPU implementation of the solver. But we didn't have much of an idea of how we could parallelize that. So that was definitely the harder challenge. Right, so the CPU code coming into this week could do in the order of tens of millions of comparisons per second per core, and can be parallelized. And that was using like hand unrolled assembler. So there was there's some room for improvement, but not much that we could see. And for the solver component, we had a very sequential, unsophisticated data structure implementation, which was solving 10,000 node graph in 5 seconds, just for an order of magnitude. The way we're computing the two, there's a distance metric called the Sorensen dice coefficient, which just computes how many bits are in common in the embeddings that we have, and a take on Kruskal's algorithm for the graph solver part, which we're calling Jacob's special algorithm. So our goal was, can we tackle both of these? And looking at how we can parallelize Kruskal's algorithm. And for our strategy for parallelizing the similarity scoring was just do a direct translation of what we were already doing from C assembler to CUDA. Yeah, very early on, I guess we worked out that doing the large-scale graph solver in parallel at all, forgetting on the graphics card, was hard. So we're looking at different algorithms, different approaches, what's been done in the past, found implementations of graph algorithms that had been published, but even in their publications, they were slower than the sequential CPU implementations. But we kind of came down to focusing on a particular subpart of the problem that we could tackle, which is the diameter or min cut of a graph. Now for the similarity calculation part, this was my first time in CUDA land. I wrote my first kernel, which was a bit of fun. The first kind of just direct approach that we did was about 1-to-1, same speed as the CPU. And we had a kernel that did one part of the computation for the entire vectors, something called the pop count. But then eventually we had one far larger kernel that tried to do all the work at once, which seemed to be a better approach. But almost like 10 times higher time was spent transferring from the device back to the host. These matrices that we work out, the distances, these pairwise distances, as I said, if you're getting all of them, it's a lot of data. And we had a couple of different approaches to solve that. The first was deciding that we didn't need all of them. These edges, only the really close entities are really going to be used in the solver. So there was a bit of a healthy tension, you could say, between the two sub-teams. The solver would like more data to use, but smaller scale would be nice. And on the similarity scoring, we would prefer to give you less data from the GPU. So eventually we moved to a sparse matrix representation. So after we compute the full dense matrix on the GPU, we converted it to sparse. Then we decided they don't really need 32-bit precision, so we threw away half of that. And then we decided they don't actually need anything above, say, a threshold, so we threw away 99% of the data by applying the threshold in the kernel as well. Some other things that we changed along the way and learnt about were things like the memory access patterns, which were mentioned in some of the stand-ups throughout the week. That was really important. Using shared memory. The first versions we had were using assembler, but we found there were intrinsics available, which was nicer. And then we found eventually we could actually get a bit more work to be done, like sorting the edges, which was more helpful for the solving component without really incurring any compute overhead. So we didn't use ACC, we didn't really write our code directly in C++, but rather we did a lot of our prototyping using cuPy, which is a Python interface to CUDA. So if you're familiar with NumPy, Python's ND array implementation, this will look very familiar to you. If data is an ND array here, applying some sort of threshold, finding indices where that threshold is positive, and then converting that to a sparse matrix, that is actually all running on the GPU. So there are asynchronous commands from our Python code, which would be sent to the GPU, and that would run that. So we found that really nice to work with. And we could also do custom kernels as well. So you'd either write a .cu file and call that from Python, or we often just had a small string of C that was embedded within our Python code, which would be compiled on the fly. The first iteration might take a little bit longer as it compiled it, of course. So computing, yeah, I guess I've kind of already covered this, that our main kernel for the similarity scoring was taking 60% of the time by the time we were done, and so that was a custom kernel, a 2D kernel going over every pairwise similarity, and then everything else was applying a threshold, downsampling, converting into a sparse matrix, and then sorting the edge weights, and then finally transferring what was left back to the host.
The original algorithm that we started with, that we currently use, is not very parallelizable, which basically forced us to consider different approaches to solving this problem. So we spent a lot of time thinking about different algorithms for doing this solving in parallel that would be reasonably easy to parallelize and also produce results of high quality. So in particular, we thought about possible ways of parallelizing the current solution, which we didn't think of anything that we thought would be effective. We considered hierarchical agglomerative clustering algorithms, but there's some issues with that, with accuracy, and Louva clustering, which seemed fairly difficult to implement. And I know NVIDIA's about to release some code, but not quite this week, which was a problem for us. So we settled on a simpler algorithm, which was basically a divide and conquer algorithm where you needed two primitives, which were a diameter of a graph and also a minimum cut function, which is basically where you partition it in two. So we decided to tackle these. Unfortunately, we didn't get very far with the minimum cut primitive, and in fact we found an implementation that claimed that the GPU code was 10 times slower than the equivalent CPU implementation, which wasn't super encouraging. However, we did implement the graph diameter function in CUDA, and we found that the graph diameter was about 1,000 times faster than the CPU implementation in NetworkX. Now, granted, NetworkX is Python, so it's not a fair comparison, but it was still way faster than what we previously had. The graph diameter itself is probably not the most optimal implementation that there can be in CUDA. In particular, look, this is non-trivial to parallelize, and there were there's a lot of accesses of random parts of memory. Like there's memory accesses all over the place, which I imagine slows things down a lot. And it currently, as it stands, needs a lot of scratch space to run this graph diameter algorithm.
So our kind of takeaway numbers would be for the similarity matrix part, which we were pretty confident could be parallelized. Luckily it could. So we're seeing what was in the order of tens of millions of comparisons is now in the low billions, so 2.4 billion comparisons per second on the P100. And yeah, so about 24 times speed up. And we do see places in the GPU CUDA implementation where it could be improved. And this is currently using one GPU. Future work there as well. For the diameter calculation, as you can see, about 0.5 seconds on the P100 versus 550 seconds on the Xeon 5. We could, obviously that means we could run larger problems on the P100 than we could feasibly get timing information for using NetworkX. So we're going to claim 1,000 times speed up there. Things we would wish for to make our life easier. A lot of the libraries in the CUDA ecosystem, because we were looking at graph libraries that exist and just trying a lot of them out, were incompatible, slightly bad experiences, shall we say, across different build tools, CUDA versions, operating systems we had access to. Really enjoyed the event. Thank you very much for organizing. Some of our stuff a lot of our stuff, our team agreed that it was a great week, and it was really nice to spend the week focusing on a single thing. And clearly we're happy that we got some performance improvements and a good understanding of where we could go from here with our particular problem. We'll definitely be continuing development on the software and this parallel stream. A lot of our stuff is completely open source, so we have our CPU implementation of the linkage software called Anonlink, and now a CUDA implementation, which we've been hacking on this week, is just on GitHub too, if you're interested. And our normal way to parallelize is on Kubernetes using lots of CPUs. And once we're happy with the GPU stuff, we'll try port that so we can use it from Kubernetes as well.